Welcome to online class lecturer. Uh, Myself V. Sudhir Gaud. I'm an assistant professor in Department AIDS at St. Martin Engineering College. Today I'm discussing about the topic about the asymptotic notation. This is one of the topic in computer science, and that is a subject name is a design and analysis of algorithms. So the algorithms point of this asymptotic notation, we are discussing this asymptotic is a representation in a mathematical terminology, and notation means it is a what exactly the acts, methods, process, and instance of the statement that is a going to use this one. So that is a first of all asymptotic notation. This is a topic about the design and analysis of algorithm. Algorithm is a procedure. Algorithm is a procedure. So what exact procedure? The step-by-step procedure to solve the problem. So that is in computer science, in a precisely and perfectly we are going to write this algorithm. So that is we are going to analyze that one. So the algorithm is a finite step of precision, precise instruction, perform the computation for solving problem. So this we are using as the algorithm. Under this one, there is an analysis part. What exactly this analysis of the what exactly we are going to use, how much memory, how much time, and how much execution purpose, so that we are going to use this mechanism. So here the comparison of algorithms, the running time in terms of the factors like memory requirements and program execution purpose that we are going to represent in asymptotic notation terminology. And here that is a what exactly the running time means the size of the program. Size of the program may be small one or infinite level. That infinite level representation is asymptotic notation. So infinite level, how much large that mechanism we are going to use. That is a mechanism we are going to use this one. So infinite level, this mechanism, we are representing the asymptotic notation. Asymptotic notation is a mathematical representation for the program solving, that is in terms of time complexity, space complexity. So the infinite level of this one, this is a mechanism we are using for the asymptotic notation. So asymptotic notation is a first of all, we are in a programming language, we are using an array. So it is a 2-dimensional array or 3-dimensional array or n-dimensional array, that representation purpose. So how much time it is going to useful for that one. That purpose we are using as a asymptotic notation. Next one is about the number of elements, in matrix. So matrix is a square matrix, that is a how many number of elements are there. So that representation purpose this we are using. Next one is the number of bits, the binary representation of input. That purpose we are using this mechanism. Next one is a vertices and edges in a graph. So now today vertices and edges graph is today is nothing but a social media network that is representing in connectivities. That connectivity we must find the time complexity. That time complexity we are using as a asymptotic notation. So this input size purpose we are finding the time complexity, running time before execution of the program. We require the asymptotic notation. Asymptotic notation is a mathematical representation for the time complexity and running the program and how much input size is required. That purpose we are going to use that one. So here there is a 3 parameters of the time complexity, that is about the we are using as a worst case, best case, and average case. The worst case, best case, and average case. Let me take as an example of linear search. These are the linear search elements, the 10, 20, 30, 40, 50. So suppose we are taking the key element 50, that is called worst. The maximum elements, whatever we are searching purpose, that purpose we are using is a worst case. So here it is a what exactly the worst case is based on the upper bound. Whenever the running time, maximum ending, whenever the upper bound, maximum ending purpose, that purpose we are using as a worst case. So it is a guarantee of the algorithm not run longer, but it is a matter of the inputs. How many number of inputs? That n minus number of that one we are finding the worst case. That is a mechanism for the worst case. For the example, I am taking as a linear search. Now comes to the best case. Whenever the key element is found in a first itself, whenever the key element found in the first itself, that is called best case. Whenever the element found in the first, that is a lower bound of the running time. The lower bound of the running times. See, example is a best case, and 50 is taken as a last one is taken as a worst case. So that is we are using as a maximum representation in a asymptotic notation. And next one is a average case. In between of first and last one, whatever the middle or whatever may be availability of getting answer is a average case. That is a predictions. That is we are predicting for what purpose. Our department is a AI and DS, artificial intelligence data science. That is artificial intelligence is a pattern recognition. And the next one is a trend analysis. That trend analysis prediction we are going to use for the future purpose. So we are using the three parameters. One is a worst case, next one is a best case, next one is average case. Worst case is a upper bound, that is a last one. And next one is a best case, that is a lower bound, that is a first one. And average case is this is a average case we are using is in between of first and last one, that is called average case. That is a types of analysis we are going to use for the asymptotic notations. Next, that is a linear search. Just now I explained about this one. Linear search, that is a parameters of linear search parameters, whatever explained, that is a worst case, best case, and average case. So that is what exactly we are using. Just now, example of linear search. So searching is what exactly we are using: binary search, linear search, Google search. These are the examples of time complexity. First attempt we are getting, that is nothing but best case. There is one comparison. That is a one comparison that we are using is one comparison. This is about we are using to found the beginning purpose. So that first key element is found, that one. This is about the one comparison is a best case. That is one of the example. Next, worst case is a last one. That is a last end of the whatever the inputs elements are there. That is the end. That is found at end. That is the end comparisons. Whatever the comparisons, end one is there. That is called worst case. Average case, in between of all these first and last one, that is a 0 to n minus 1. That is the n plus 1 by 2. That is the average case. This is the examples we are using for the time analysis. Now comes to our mechanism is a linear search or linear type 1. Say what exactly? Certain mechanisms are there. So we are sortings are there. That is about the selection sort, insertion sort, merge sort, and quick sort. So here it is a worst case, average case, and best case. So that is a whatever the selection sort, we are selecting from the different comparison purpose. What we are selecting, a card or whatever may be item or whatever may be, we are selecting. So that comparison purpose, any type, n square. So the for loop is there, n plus 1. Next for loop is there, n plus 1. That mechanism, that is a worst case. Same way, best case is a n square. Next one is about the n plus 1, n square. So all three for the selection sort, we are using this one. Next one is about the insertion sort. Insertion sort, just like we are playing a card, how we are inserting one by one for the sequence purpose. That sequence purpose we are using as a insertion sort. So that insertion sort is what exactly our time complexity, n square for the worst case and n square for the average case. That is a best case is a n. What we are inserting, best one is the first one is there, that is called n, that's all. So that is a insertion sort we are using. And next one is about merge sort. Merge sort is a design of analysis of algorithm, is one of the best method is a divide and conquer technique. Under divide and conquer technique, we are using as a merge sort. So merge sort mechanism is first of all, it is a partition, divided whatever the merging of that one. So that is what exactly we are using worst case, that is a n log n. So whatever the first part of that one division, we are adding that one n log n. Next one is about the average case is a n log n, and next one is a n log n. All three parameters, best case, worst case, average case, is n log n mechanism. So this is we are using as a merge sort. Next one is a quick sort, that is about the, we are using n square for the best case and n log n for the worst case, and next one is n log n for this one. So this mechanism we are using the types of analysis example of for finding for the complexities of using asymptotic notation. So we need the, what exactly, why we require the algorithms. First one we can do the small mechanism, second one do the big mechanism. So that purpose, comparison purpose, we are using asymptotic notations in a mathematical terminology that is called functions. That function should be written in a limited, that is calculus. That calculus should be executed comparison within long term or short term or medium term or a bond term, which term. That purpose we are using the asymptotic notation. Asymptotic notation is a mathematical representation for the to find the time complexity or runtime program or growth rate purpose, where it is a infinite level we can find out the asymptotic notation. So that purpose we are using the asymptotic notation. So first of all, two functions are there, we must compare that one. So what exactly? Compare the execution times. So specific particular computer, sometimes we are using normal instructions, sometimes we are using a functions, maybe recursion function or any other functions. So very fastly we can solve that one. So that purpose we are using. Always successful in the, not in one format. We are using a lot number of control structures like if statement or selection case study, like that one. This mechanism we are using. Next one is about the number of counts of the statements, number of counts of the statements. That purpose we are using. So this is very within the number of statements. That purpose we are solving the mechanism. That purpose we are solving. So here that is representation in terms of mathematical terminology. In terms of mathematical terminology, the function. So the function is a representation, the running time of the function with the input size, n size, input size, n size purpose we are using. The running time of the function, input n size, that purpose we are going to solve. The compare with the different functions, f of one function, g of another function, what is the difference based on that one? That purpose we are using as a asymptotic notation. That is a we are using the corresponding running time. So such an analysis may be machine dependent or machine independent or whatever may be access, and what type of application we can go into add this one, and what machine time programming style, and this types of process. So it may be how far this one is structured programming or OOPS programming. That purpose we are going to use the asymptotic notation. So here certain algorithms are there. So that algorithm based on that one, we are going to use the asymptotic notation. First of all, time cost for each statement, how much time is going to take place. How much time is going to take place. That purpose we are using as a asymptotic notation. So total cost of the number of times of the each statement, how much total time is going to take place for the this mechanism. So that is a we are using as asymptotic notation, this mechanism we are using. So algorithm is written, first one, the array at 0 size, that is 0, 1, array 1 is 0, array 2 is 0, and array n minus 1, the size is n minus 1. So how these are the statements are there, cost 1, cost 1, cost 1. So that is a mechanism is a cost into n number of times. So it is a, this is a n number of times is a time complexity. This time complexity is whatever the cost is there, n number of times that is going to take place. This is for the future point of view I am explaining. So this is about the big O n, that is a mechanism for the this one. Why? Because n number of times, this is n number of times. So C1, 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 that is a n is there, no? So that is a n number of times, this we are using this one. Next mechanism, same formula, same method of whatever the problem solving, we are using the for loop. We are using the for loop. So what exactly? I is equal to 0 and that is a I is less than n and I plus plus. This mechanism, what exactly we are using as a the number of times, that is n plus 1 number of times for loop it is happening. So n is a maximum 1, I plus plus is a postfix operator. So that is these number of times it is happen. So that is a mechanism as n plus 1. So this So this is a what exactly we are using the total value of this one n plus 1 and n. So which is a maximum one? 2n. That n is a maximum one is a we are using is big O n. That purpose, the time complexity purpose, we are using the algorithms for the asymptotic notation, mathematical representation, simple terminology, very easy to understand. That purpose we are using. As here about the algorithms are written, so there is a two for loops are there, two for loops. One is about the for loop for the ith row and next one is about the jth column, means matrix type one. So the for loop mechanism for the number of counts is a number of counts is next one is a n plus 1. So these are the two for loops n plus 1, n plus 1. That is a what exactly here that C1 and C1 is the first count and C2 is the second count n plus 1 and next one is n into n plus 1. So that is a what exactly this mechanism is happening. So this is a we are using as a n plus 1 into n plus 1 whole square. That n plus 1. So that is a mechanism is a what exactly this is happening. N square plus 1 plus 2n. So that is a maximum one. Maximum one. That is what is maximum one? N square. N square of this algorithm time complexity is taking place. Maximum one we must take. So which among this one maximum one is a that is a n square. So big O n square is a time complexity for the solving the problem n square. That purpose we are using as an algorithm. Under algorithm time complexity running time. So this purpose we are using for the asymptotic notation. Now what exactly we are using as asymptotic notation? Now comes analysis part. Now comes the analysis part. So analysis part is what exactly we are representing in the mathematical terminology. What type of mathematical terminology? We are using the functions. So what is the first function? Compare the two algorithms in a running time of function f of n and next g of n. So the compare with these two and we are measure the character is how fast which one f of n will come first or g of n will come first. That purpose we are using as a asymptotic notation. So what exactly we are finding for the how much growth rate? How much growth rate? So that is a growth rate. So we are using for the growth rate purpose. The growth rate purpose we are using as asymptotic notation. And here compare the functions under what type of calculus limit under this one, the asymptotically, that is mathematical representing. So for functions, that purpose we are using this mechanism. So what are the infinite level of large level, we are going to solve that one. Infinite level, large level, that purpose we are using. So here some mechanism for the growth rate. We are using certain statements. So that statements are written in this format and we are using approximation. The n to the power of 4, that is a equation n to the power of 4, 500 and that is a 100 plus 10n and 50. So maximum one is n to the power of 4. This mechanism we are using. So this is we are using for the finding for the solution. That is asymptotic notation. We are using as this mechanism. Here the growth rates of given certain mathematical terminology, constant is a highest priority. Next one is a log n is the second one. Logarithms is the second one. That purpose we are using. Next one is a log square n. That is we are using third one. Next n log is a linear equation, linear search, that type of application. Fourth one n log n, mostly sorting type one or searching type one. So n log n, that mechanism we are using. N square, that is a ax square plus bx is a what exactly example? It is a quadratic equation. N square is a quadratic one. Next one is a cubic, the n cube. next n to the power of 4, like that one terminology we are using. Final one is a exponential one. Final one is a exponential one. So from constant to exponential, the time complexities we are going to find out in a growth rate of an algorithm. That purpose we are going to use the asymptotic notation. So this is an example we are using. So here the growth rate of complexities are given. Here class n is equal to 2, n is equal to 16, n is equal to 256, n is equal to 1024. And here constant 1, that is the 2 to the power, the 1 to the power of 1, 1, 1 anytime. So it is always 1 will get it. Next one is log n, that is the n log 2 to the base 2 and 2, that is value is 1. And that is a log base 2 to the power of 16. Why? Because it is a 2 to the power of 4. 4 value get it. 256, 8, like that one. We are getting the results, the growth rate of the classes. We are getting the results, growth rate of the classes. So like that one, n log n, this is we are using this mechanism. Here certain examples is given. Sometimes it is going for the days, like that one. So here's what exactly n square, n cube, like that one. Time complexities, we are going for the large infinite level of the problem. That purpose we are going to solve that one. Now comes to the time complexities about this one. So this is a big O notation, less than, and next one is that is what exactly, this is a mechanism. This is a big O notation. F of n is equal to big O of g of n. F, that is implies f of n less than or equal to g of n. This is a mechanism for the big O notation. Next one is a omega notation, big omega notation. That is a what exactly, greater than. That is a f of n greater than or equal to g of n. So that is a f of n is equal to omega of g of n. That implies f of n is greater than or equal to g of n. That is greater than. Next one is about the theta notation. That is equality. F of n is equal to theta of g of n. That is a f of n is equal to g of n. So this is a mechanism for the time complexity of the major 3 or important one that we are going to use for the asymptotic notation. Next one, a little o, little omega also there. But among these 5, big O notation is a major using application. That purpose we are going to use we are using this mechanism. So whatever the big O notation, it is a big O notation, that is a mechanism we are using this one. Under this mechanism, f of n is equal to less than or equal to g of n, and f of n is greater than or equal to g of n is a omega notation, and f of n is equal to g of n. That is a, we here f of n g of n less than or equal to g of n is a worst case. Worst case is what exactly, maximum extent we are using, and it is a upper bound, and we are selecting the utmost position. We are selecting the utmost position, and whereas this one, f of n is greater than or equal to the g of n, that is a best case, means first itself, it is a lower bound, and it is a mechanism is a at least. So minimum level only we found the element, that is we are finding this one. Next one is about the f of n equal to g of n, that is about the, it is a mechanism, this is a we are using is a average case, means the tight bound. It is a low, that is what exactly, it is a we are using as a worst case, best case, and average case. Next one is maximum, minimum, and average, and that is a we are using as a this mechanism is a worst case mechanism, best case mechanism, and average case mechanism. So big O notation, here certain examples are given. So that is a f of n is equal to 30n plus 8. So what exactly under this one, n is a maximum one, that we are taken as a big O notation. That we are taking as a big O notation. It is almost roughly proportional to the n. that is almost roughly proportional to the n. And next one, n square, that is a what exactly in expression is like quadratic expression. So that is a big O n square, that is at most roughly proportional. So that is a n square. Next one is about the what exactly, that is n square is a faster growing purpose, that big O notation we are using. So this is a mechanism for the big O notation. This graph is there. So what exactly, that is a one function is a what exactly, that is a f, first function f of n is equal to 30 n plus 8. Next one is the f of b n is equal to n square plus 1. So this is a mechanism, this we are using. Here, these are three types of notations are there. Under this one, graphical representation, that is an example about the big O notation. This is about the big O notation is a whatever the function is there, upper bound. This is a upper bound. So whatever the function is there, that is f of n, that is a, we are using f of n less than or equal to c of g of n, or f of n is equal to O of g of n. This is a mechanism we are using. That is about the upper bound. That is about the big O notation. Here maximum, in maximum type 1, that is the at most position purpose, we are using this mechanism. At most position purpose, we are using this mechanism. So big O notation we are using is a at most position, that is a worst case, and maximum style. And next one is the upper bound purpose, that is a big O notation. Next one is about the omega notation, that is a, we are using is a lower bound, the whatever the given n size of the whatever the elements. Next one is a time taken for this one. So the what exactly, this is a lower bound. This is about the notations we are using, isototic notations. Among the three are important one. One is about the isototic notation, about the big O notation, omega notation, and theta notation. That is a, whatever the omega notation is a mostly upper bound, that is application is called upper bound, and omega notation is a lower bond, that is a lower bond, and this is a tight bond. This is about the tight bond. So this we are using as a mathematical representation for the algorithm time complexity purpose we are solving. And next one is about the, we are using a maximum purpose. This is a, whatever we are using is a maximum purpose. That is a bond for the this big O notation. Next one is a minimum purpose. This is what exactly minimum purpose, this we are using. Next one, and this average purpose. This average purpose we are using in between of these two functions that we are using. Next one is about the, we are using this one is a at most purpose, that is a what exactly at most, that level we are using. This is a at least, that is a mechanism of the function at least. And this is a tight bond, this is about the tight bond between this application, that is a, we are using this mechanism. So big O notation we are using as a that is about the big O notation we are using for the maximum purpose, that mechanism we are using. And next one is a minimum purpose we are using. And next one is the average tight bound purpose, that application we are using for that this mechanism. So function is f of n less than or equal to c of g of n. Function that is a f of n less than or equal to c of g of n. That is called big O notation. Whereas a function f of n less than g of n, here not equal condition. Here not equal condition. That is a mechanism we are using. Yes, here it is about the big O notation, that mechanism we are using this one. And what exactly that is mechanism is we are using as a, that is g of n is more than the this mechanism for the omega notation. This is about the omega notation, that is a big O notation. So that we are using this mechanism. So that is a notations we are using as omega 1. F of n is less than of g of n. This is a we are using as a omega notation. And the next one is about the theta notation. So theta notation is in between of theta notation, that is in between of C1 g of n less than or equal to f of n less than or equal to C2 g of n. That purpose we are using as these three application purpose, that is a theta notation. So these three are we are using as a asymptotic notations. And little o, little omega notation. Little o notation is f of n less than c of g of n. It is not equal, less than, that is a little o notation. Today I discussed about asymptotic notation in a design and analysis of algorithm. Thank you for my class about I taught the asymptotic notation.